Have you ever wondered how an AI actually learns to win at something like chess? Or how a self-driving car makes that split-second decision on when to turn? Well, it turns out they're both built on the exact same fundamental idea. And today, we're going to pull that idea apart and see how it works. We're talking about the Markov Decision Process. So, how do you teach a machine to think, really? I mean, you can't just program in every single possible outcome. That's impossible. The trick is to build a system that can learn from its mistakes, adapt, and figure out the best way forward all on its own. The real question is, how do we even start to build something like that? You know what? To really get this, let's just build one. We'll start from scratch. So I want you to picture a simple little robot dropped into a maze. It has one single goal in its entire existence. Find the cheese. It sounds almost silly, but trust me, this simple setup has all the key pieces we need to understand how even the most complex AIs actually think. Alright, let's get into it. Every problem like this, at its very core, has two main characters. First up, you've got the agent, that's our robot, the one making all the decisions. And then you have the environment, that's the maze itself, the world our little agent needs to navigate. Now, for our agent to do literally anything useful, it needs a couple of basic tools. It has to know where it is, and it has to know what it can do from there. And that brings us to two absolutely crucial concepts, states and actions. So, a state is really just a fancy way of saying, what's the situation right now? Think of it like a single snapshot of the world from the agent's perspective. If anything important changes, boom, you're in a new state. It's like one frame in a movie. And for our robot, it's super simple. Every single square in this maze is its own unique state. Being in the top left corner is a totally different state than being in the square right next to it. That's all the agent knows. I am in this specific square. So if a state is where am I, then an action is what can I do about it? It's just the menu of possible moves the agent can make. For our little robot, that menu is pretty short and sweet. It can try to go north, south, east, or west. Okay, so our robot knows its location and its possible moves. But how does it ever learn that going east is a good idea and walking into a wall is a bad one? Well, this is where the environment lays down the rules of the game, and it does that with two things, transitions and rewards. Now, here's a really important idea. The world isn't always 100% predictable, right? And a transition probability is how we deal with that messiness. It basically just tells us, hey, if you take this action, here's a chance you'll end up here, and here's a chance you'll end up over there. It's all about the odds. Let's make that concrete. Our robot decides to move east. In a perfect world, it just moves one square east. But maybe the floor is a little slick, so there's a 90% chance the move works exactly as planned, but there's a 10% chance its wheels just spin and it doesn't go anywhere. It stays in the same state. That bit of randomness is what transition probabilities are all about. So, how does the robot even know if slipping was a good thing or a bad thing? Well, that's where the reward comes in. It's just a number, a score, that the environment gives the agent right after it moves. Think of it as instant feedback. A positive reward is like a good job, and a negative reward is a nope, don't do that again. Okay, now this part is just brilliant. This is how we actually shape the robot's behavior. So, of course, reaching the cheese, that's a big plus 10. Awesome. Hitting a wall? Ouch, -5. That's a penalty. But look at that last one. Taking even a single step costs it a tiny bit, -1. Now, why would we do that? Well, think about it. This little penalty pushes the robot to not just find the cheese, but to find it in the fastest way possible. Without it, the robot might just wander around forever, happy as can be as long as it didn't hit a wall. That -1, that's the secret sauce for efficiency. Alright, so we've got all our Lego bricks, states, actions, transitions, rewards. But how does the robot actually put it all together to make a choice? This brings us to the most important piece of the whole puzzle, the policy. A policy, which you'll often see written as the Greek letter pi, is basically the agent's brain. It's its complete strategy for the game. It's a map that says, for every single square on this board, here is the exact action you should take. If you're here, go north. If you end up over there, go west. No thinking involved, just follow the map. Honestly, this is the best way to think about it. You know those old school strategy guides that told you the absolute perfect move to make to beat any level? A policy is exactly that, but it's for our AI. But, obviously, not all strategy guides are created equal. A really bad policy might tell the robot to just walk into a wall again and again, or go in circles. The whole goal, the entire point of all this is to find the optimal policy, that one perfect strategy that will rack up the most points, the most reward over the long haul. And that's really the key takeaway. The whole purpose of this kind of AI, what we call reinforcement learning, is just to find this one perfect policy, often called pi star. Every fancy algorithm out there is just a different tool for solving this exact puzzle, for finding that ultimate strategy guide. So, a robot finding cheese. Cute. But let's see how this simple idea blows up to solve some incredibly complicated real-world problems, because, as you can imagine, it's not just about finding cheese. The amazing thing is how flexible this framework is. For an AI playing the game Go, a state is just the pattern of stones on the board. An action is where you place the next stone. And the reward, well, that's winning the game. For a factory robot, the state is the position of its arm. Actions are tiny movements, and the reward is a path that's perfectly placed. For a trading bot, the state is all the market data. Actions are buy or sell, and the reward, well, that's cold hard cash. It's the same logic, just applied to totally different worlds. And that's really the magic of it. States, actions, rewards, and policy. These four simple ideas are so universal that they can be used to describe almost any decision-making problem you can think of, from a simple maze to something as complex as managing an entire country's power grid. So that leaves us with a pretty big thought, doesn't it? We've created a system that allows an AI to find the perfect strategy for any game, as long as we can define the rules, the available moves, and what it means to win. And as we get better and better at defining those things for more complex parts of our reality, you have to ask yourself, what's the next game we're going to ask it to solve?